Okay, my dear students, in the previous class we learnt about the lubricants and its properties and then functions of lubricant and so on. And in the second video, that is part 2 video, we learnt about various bearing materials and various properties of bearing materials, and also we learnt about mechanism of lubrication and pressure development in an oil film in hydrodynamic lubrication. Now, moving on further from here, we are going to learn about Newton's law of viscous flow. So here, basically what we need to consider is consider a journal bearing. This is the journal, which is the rotating part, and bearing is the stationary part. And in between we will have fluid, and we know this is the convergent film and this is the divergent film. Now what I do is, I will take a small element from this zone, whatever zone is the journal bearing. So journal is the moving element and bearing is bearing is the stationary element. I just take one small piece of this journal bearing combination out here. So you have journal, you have bearing, and in between you will have fluid. So moving surface is what? This is the part of journal, and this is the stationary surface, which is the part of bearing. Between the moving surface and the stationary surface, we have got the fluid present. Okay, so just consider an oil film, thin oil film, whose cross section is denoted by ABCD, which is a rectangle, and at laminar flow conditions, this film after some time will be displaced to A1, B1, C1 and D1. This displacement of each point of the element is proportional to the distance from stationary surface, that is depicted over here. So more the distance from the stationary surface, more is the shear that it is subjected to. Okay, so that is, we have moving surface, which is essentially representation of journal. We have stationary surface, essentially the representation of a bearing. Between journal and bearing, we have got fluid. So fluid after some time will move or will change its shape from ABCD to A1, B1, C1, D1, and this change in shape depends upon distance of the fluid film from the stationary surface. Okay, now the rate of shear or in the film, okay, is du by dy. I have just considered an element of an oil film moving with velocity of du and thickness of oil film as dy. So the rate of shear depends upon rate of shear is given by du by dy. Since the rate of shear in the oil film is a constant value for any point in the film, I replace du by dy by u by h, where h is the clearance, that is the distance between the moving surface, that is journal, and the stationary surface, that is essentially bearing. And we have learnt according to Newton's law of viscous flow, at any point in a fluid, the shear stress is directly proportional to the rate of shear. This is according to Newton's law of viscous flow. The shear stress at any point in a fluid film is proportional to rate of shear. I remove this proportionality symbol and I am going to get a constant. This constant, the eta, is called the absolute viscosity of the fluid, and its unit is Pascal second or Newton second per meter square, and then the absolute viscosity eta, I can write it as shear stress by rate of shear. Fine. Please note down this much into your notebook.